The roar of four massive engines tore across the airfield as Japan's first heavy bomber, the Nakajima Shenzhen, began its desperate struggle down the runway. At 44,713 pounds empty, it carried nearly 8,000 pounds more weight than America's B-17 Flying Fortress. The test pilot wrestled with controls that felt sluggish and unresponsive as the enormous aircraft finally lifted away from the concrete, climbing at an agonizing 500 feet per minute, half what American bombers could manage. Down below in the hangar, Chief Engineer Kenichi Matsumura tracked the aircraft through his binoculars, watching it fade into the morning haze. His notebooks lay open on a workbench filled with calculations that should have prepared him for exactly this moment of disappointment. Japan had purchased the DC-4E prototype back in 1939 for $275,000. The Navy had been convinced they'd obtained the secrets to American aerial dominance. 2 years of painstaking reverse engineering followed. Hundreds of skilled workers, the finest materials Japan could spare, all devoted to replicating American technological excellence. Yet as the Shenzhen disappeared into the clouds, barely holding altitude, the brutal reality crystallized. Sometimes copying isn't enough. You need to understand the thinking behind what you're copying. The date was April 8, 1941. Morning light stretched long shadows across Oda Airfield as Matsumura checked his stopwatch. Today he'd witness what the Imperial Navy believed would be their answer to American strategic bombing power. The Nakajima G5N Shenzhen sat at runway's end, a metallic mountain waiting to prove itself. Its 4 radial engines already rumbled to life, producing deep, throaty sounds that traveled through the concrete beneath his feet. Matsumura had devoted 18 months overseeing every rivet and circuit of this machine, driven by an obsession that had gripped Japan's entire aviation industry since Pearl Harbor planning had begun. The Americans possessed something Japan desperately lacked: the ability to strike industrial targets from 2,000 miles away. The B-17 Flying Fortress held everything Japan needed, everything they were missing: reliable engines, fierce defensive firepower, most crucially the range to carry war across the Pacific to enemy territory. Major Katsuaki Kira sat in the cockpit now, running through his pre-flight checks. The bomber stretched 138 feet nose to tail, its silver aluminum skin brilliant in the early light. On paper, the numbers looked impressive: 4,000 kilograms of bomb capacity, 3,500 miles of operational range, defensive guns positioned to rip apart any interceptor. Navy procurement officers had called it Japan's war winner, the aircraft that would crush American industry. Yet Matsumura's engineering notebooks revealed troubling truths he'd wrestled with for weeks. Empty weight, 44,313 pounds. But captured B-17G intelligence reports showed American bombers at just 6,135 pounds without fuel or ordnance, 8,000 pounds heavier for identical missions. This violated everything he'd learned across 20 years of aircraft design. The 4 radial engines reached full throttle with a sound like continuous thunder, each producing 1,170 horsepower, 7,480 total horsepower to lift 62,500 pounds at maximum takeoff weight. Matsumura calculated the ratio instantly: 120 horsepower per 1,000 pounds. The B-17G achieved 133 horsepower per 1,000 pounds with its right cyclones. And those American engines had proven themselves through hundreds of combat missions across Europe, operating without complaint. Major Kira released the brakes. The Shenzhen began its takeoff roll, gathering speed slowly at first, then with momentum that seemed endless. 1,000 feet consumed, 2,000, 3,000. Matsumura's stopwatch ticked forward as the bomber used up 4,200 feet of concrete before the nose gear finally lifted off. A B-17 needed 2,200 feet, half the distance, and with superior reliability to boot. The Shenzhen climbed grudgingly, rising at barely 500 feet per minute, while Major Kira fought controls that resisted every input, like he was pushing through thick oil. Through his binoculars, Matsumura could see the pilot's helmet turning constantly, compensating for the bomber's tendency to wallow rather than fly with purpose. American B-17s climbed at 900 feet per minute. Their crews reported the aircraft felt eager, hungry to reach altitude. As the Shenzhen melted into the haze, struggling to maintain even its laboring descent, Matsumura suddenly grasped the magnitude of Japan's error. Back in 1939, Japanese negotiators had purchased the Seoul DC-4E prototype for $275,000, convinced they'd bought the formula for American aviation supremacy. The massive four-engine airliner seemed perfect for military conversion. 138 feet of wingspan, all-metal construction, tricycle landing gear, four powerful engines arranged like the B-17. But American Airlines had rejected it entirely. United Eastern American Airlines all examined the prototype and concluded it was overbuilt, over-engineered, fundamentally unprofitable. The aircraft Japan thought represented American technology at its peak was actually American industry's most expensive flop. Matsumura's team had reverse-engineered every component with surgical precision, assuming American designers had valued raw strength over efficiency. They reinforced structures that were already overbuilt. They added defensive positions that increased weight without adding capability. They installed engines producing adequate power but lacking the reliability needed for sustained combat. Those radials quit every 50 flight hours, demanding complete overhauls that consumed precious materials and irreplaceable skilled workers. Wright Cyclones in American service routinely ran 400 hours between major maintenance. The irony cut deep. Japan had spent 2 years and millions of yen copying an aircraft Americans had abandoned as commercially useless, then made it heavier and more complex in the name of military adaptation. Every number in Matsumura's notebooks confirmed what the test flight demonstrated. The Shenzhen was fundamentally broken. Magnificent engineering applied to a faulty foundation. Radio static crackled from the control tower as Major Kira reported his position 20 minutes into the flight. Service ceiling testing would follow, but early signs suggested the Shenzhen would barely reach 24,000 feet in combat conditions. B-17s cruised routinely between 25 and 30,000 feet, using altitude itself as defense against interceptors. American bombers operated in an altitude band where Japanese fighters could scarcely follow, transforming the sky into protective terrain. Walking back toward the engineering hangar, Matsumura's mind raced through the implications. Japan needed strategic bombers desperately, but copying American hardware proved insufficient. The DC-4E purchase had assumed that possessing enemy equipment automatically transferred enemy capability. But capability lived not in blueprints. It lived in the industrial philosophy creating those blueprints. American aircraft designers didn't simply build flying machines. They built machines that could be manufactured by the thousands, serviced by minimally trained mechanics, operated reliably in combat by 20-year-old crew members. Japanese engineers built masterpieces demanding constant attention from skilled craftsmen. Technically sophisticated, but operationally fragile, the Shenzhen would never see production. Even as Major Kira prepared for landing, Matsumura knew Japan's first attempt at copying American strategic bombing had failed from the beginning. But failure, he understood, could teach lessons success never would. Spring arrived at Nakajima's Koizumi facility, carrying renewed urgency. The Imperial Navy remained absolutely convinced Japan's bomber program could still deliver victory. Despite the Shenzhen's disappointing flight, Admiral Isoroku Yamamoto's staff issued new directives bordering on the impossible. Develop a heavy bomber reaching the American mainland within 18 months, or watch Japan's window of opportunity slam shut forever. Matsumura found himself working 16-hour days, his engineering team expanding to over 200 specialists pulled from every major aircraft project in Japan. Navy leadership's faith remained unshaken, based on specifications that looked formidable on official procurement documents. 4,000 kilograms of bomb capacity, 500 miles of operational range. Defensive armament, 4 20mm cannons and 12 7.7mm machine guns. On paper, the aircraft could devastate American industrial targets from Alaska to California. But Matsumura's test data told a darker story, growing more troubling with each mission. The Shenzhen's maximum speed of 261 miles per hour made it prey for any modern fighter. Its service ceiling of 24,150 feet exposed it to interceptors attacking from above unchallenged. Captured intelligence reports showed American P-38 Lightnings reaching 39,000 feet and exceeding 400 miles per hour in dive attacks. Engine reliability proved even worse than performance shortcomings. Radials required complete overhauls every 50 flight hours, consuming aluminum alloy Japan could barely spare. Each engine contained precisely machined parts demanding Japan's most skilled workers, men desperately needed for zero fighter production as the Pacific War expanded. Worse, the power plants generated severe vibrations, loosening instruments, cracking fuel lines, fatiguing airframe structures at terrifying rates. Wright cyclones in captured B-17s showed maintenance intervals consistent with 400 hours of operation between major service. American engine philosophy emphasized reliability over peak power, accepting slightly reduced output for dramatically superior operational readiness. A B-17 squadron maintained combat readiness for months. Shenzhen bombers spent more time in maintenance hangars than on combat missions. Matsumura's team began detailed examinations of Wright R-1820 engines removed from downed B-17s in the Philippines, and the manufacturing philosophy differences were instantly obvious. American cylinders used simple cooling fins mass-produced on automated machinery. Japanese engines featured complex cooling patterns requiring individual hand finishing by master craftsmen. American connecting rods were forged from standardized steel alloys. Japanese rods used exotic metals, improving performance but creating bottlenecks. The problem extended beyond components to the entire industrial approach. American manufacturers designed for mass production from the initial sketch stage, creating aircraft assemblable by minimally trained workers using standardized tools and procedures. Japanese designers optimized for performance and craftsmanship, creating machines requiring skilled artisans at every stage. The result was bombers performing magnificently when new but degrading rapidly under combat stress, demanding constant attention from specialists increasingly impossible to replace. By the summer of 1941, the Shenzhen program had devoured resources that could have built 300 Zero fighters, yet it had produced just 6 experimental aircraft. What planners had deemed reasonable production targets during peacetime suddenly seemed hopelessly inadequate as the war spiraled far beyond anyone's predictions. Meanwhile, American factories were churning out B-17s at a staggering 20 aircraft monthly from single plants, with additional facilities standing ready to activate as military demands climbed. From its earliest test flights, the Shenzhen battled a weight problem that only worsened with each new system added. Protective armor around vital components added 1,200 pounds of dead weight. Enhanced guns and ammunition brought another 800. Self-sealing fuel tanks, absolutely critical for survival in enemy airspace, ballooned the aircraft's empty weight by another 1,500 pounds. Each improvement meant to boost combat effectiveness, strangled performance in a cruel cycle where the very protections meant to keep the bomber safe made it too sluggish to escape danger. Matsumura's numbers revealed something terrifying. A fully loaded Shenzhen at maximum fuel and bomb load would struggle simply to stay airborne if even a single engine quit. Flying on 2 engines presented genuine hazards. Single-engine performance was marginal at best, making landings precarious. Yet intelligence reports showed B-17 crews routinely limped home on half power, sometimes bringing their damaged birds back after losing engines to enemy fire. Japan faced another crushing problem. Aluminum scarcity began striking all Japanese aircraft production by late 1941, but the Shenzhen took the heaviest blow. A single Shenzhen consumed 8 tons of aluminum compared to 5 tons for a Zero, or just 3 for a standard army bomber. Japan's entire aluminum output could theoretically supply 12 Shenzhens monthly, but only if no other aircraft rolled off production lines simultaneously. Wartime reality meant heavy bomber construction competed directly with fighter production needed desperately for home defense. American aluminum output surpassed 900,000 tons yearly by 1943. Japan peaked at 142,000 tons in 1944. That resource gap rendered large-scale bomber construction impossible. No matter how cleverly engineers designed, Even a flawless aircraft couldn't solve what industry itself couldn't deliver. The toll on Matsumura's team grew heavier as each test flight exposed fresh problems. Engineers watched their painstaking work on individual components get undermined by fundamental design flaws that no refinement could overcome. Complete redesign was the only answer, but Navy schedules left zero time for starting fresh. By autumn, Matsumura grasped a terrible truth he couldn't speak aloud in official settings. Japan was building the wrong aircraft through the wrong methods for the wrong war. The Shenzhen embodied everything Japanese engineering excelled at: precision work, meticulous attention, perfectly optimized parts. But it needed what Japanese industry handled poorly: mass production, simplified maintenance, ruthless reliability over perfection. Captured B-17s sitting in Japanese hangars offered a daily lesson in a completely different approach. Yet understanding American philosophy and implementing it were worlds apart. Japan possessed the technical knowledge. What it lacked was the industrial machine to produce enough of them to matter. The captured B-17E arrived on flatbed trucks at Nakajima's facility in March 1942, its aluminum skin scarred by fighter cannon fire that had brought it down over the Philippines. Kenichi Matsumura stood watching as workers carefully guided the intact fortress through the hangar doors, feeling anticipation mixed with dread. For 18 months, his team had reverse-engineered the DC-4E, thinking they grasped American design thinking. Now they would meet the real thing. The fortress seemed smaller than expected. Its 103-foot wingspan appeared almost fragile beside the Shenzhen's massive 138-foot spread. But as inspection began, genuine differences emerged that shattered every assumption about American engineering. The B-17's empty weight of 36,000 pounds was 8,000 lighter than the Shenzhen, despite similar defensive guns and fuel capacity. Matsumura personally oversaw engine extraction, watching technicians carefully remove the right cyclone radials that had powered this particular fortress across thousands of Pacific miles. Each engine weighed 1,850 pounds and delivered 1,200 horsepower at takeoff. The Shenzhen's engines weighed 2,100 pounds each, but generated 1,870 horsepower. The power ratio looked impressive until measured against American efficiency. Those cyclone engines bore wear patterns that revealed remarkable operational durability. Cylinder walls showed even wear matching hundreds of flight hours. Rod bearings showed minimal wear despite obvious combat punishment. Most stunning was cooling system simplicity. Straight fins cut by automated machines rather than complex curves Japanese engineers had considered essential for heat control. Dismantling American engines exposed manufacturing philosophy, contradicting everything Matsumura learned about precision. Tolerances seemed loose by Japanese standards, yet they ran more reliably than memory radials built to much tighter specs. American designers had optimized for consistency rather than peak output, accepting slightly lower efficiency for dramatically better maintenance. Airframe construction revealed even deeper insights. B-17 wing spars employed aluminum extrusions from rolling mills with reinforcement concentrated at critical stress points rather than distributed everywhere. Japanese Shenzhens used complex forgings demanding individual machining, theoretically superior but practically impossible to produce in volume. Matsumura spent hours examining B-17 electrical systems, stunned by standardization allowing any component replacement with minimal training. Color-coded wire insulation and standard connectors eliminated guesswork during fieldwork. Cables ran through accessible channels with inspection ports at intervals for quick troubleshooting. Shenzhen electrical systems required specialized knowledge, custom connectors, and hidden routing that made repairs painfully slow. Gun installations told another story. B-17 positions allowed rapid installation and removal with universal mounts for different weapons as missions changed. Ammunition feeds used simple mechanics, rarely jamming even under violent stress. Japanese armament demanded precision and firepower with complex hydraulics, providing better accuracy but requiring constant specialist adjustment. Flight controls operated through simple cables and pulleys, almost primitive against Japanese hydraulic systems. Yet American pilots reported excellent handling everywhere. Mechanical controls gave direct feedback, letting pilots sense approaching stalls. Hydraulic assist could mask dangerous attitudes until recovery turned impossible. Simplicity wasn't inferior engineering, Matsumura suddenly understood. It was superior design thinking. Fuel systems made American priorities brutally obvious. B-17 tanks used simple aluminum with replaceable rubber bladders serviced with basic tools in field conditions. Self-sealing came from rubber compounds automatically closing small punctures without complex mechanisms that failed under combat stress. Japanese fuel systems used sophisticated pumps and valves, managing fuel precisely, but creating multiple failure points, stranding aircraft far from bases. Through summer 1942, as analysis accumulated, Matsumura grasped Japan's strategic error. American engineers weren't building individual aircraft. They designed production systems, manufacturing thousands using workers with limited training. Every part was optimized for mass production, field maintenance, ROI, and operational reliability rather than peak performance or engineering elegance. Numbers told a devastating story. B-17 production had reached 48 aircraft monthly at Boeing's Seattle plant alone, with additional lines planned. Each bomber required roughly 15,000 man-hours versus 32,000 for one Shenzhen prototype. American workers built 3 flying fortresses in the time Japanese craftsmen needed for one heavy bomber. Material comparisons proved equally grim. B-17s consumed 5.2 tons of aluminum, while Shenzhens required 8.1 tons for comparable capability. American designers eliminated unnecessary material through stress analysis, creating structures exactly strong enough operationally without excess weight destroying performance. Japanese engineers built structures stronger than needed, believing excess strength always beat optimized design. Maintenance philosophy appeared through recovered logbooks from the crash site. B-17 squadrons performed scheduled maintenance using standardized procedures any trained mechanic could complete in the field. Engine changes took 6 hours with common tools. Hydraulic repairs required only basic knowledge. Shenzhen maintenance demanded specialists understanding unique characteristics of each aircraft, making squadron-level repairs impossible during combat. Most revealing was American battle damage repair thinking. B-17 structures failed gracefully with damage concentrated at specific points, patched with field expedients. Aluminum skin panels got replaced with sections cut from other aircraft, while structural repairs used standard aluminum stock from any industrial supplier. Japanese aircraft demanded custom parts manufactured precisely, making field repairs impossible and forcing damaged aircraft out of service for months. By October 1942, Matsumura reached conclusions that would reshape Japan's bomber approach entirely. The B-17 wasn't superior through advanced technology or exotic materials. It excelled because American engineers solved the correct problem. Instead of building the perfect bomber, they built bombers that ordinary people could manufacture, maintain, and operate under extraordinary circumstances. The path seemed clear yet daunting. Japan needed abandoning the Shenzhen program completely and starting fresh with American design thinking as foundation. But 18 months into the Pacific War, time for fundamental changes was evaporating. The telegram from Imperial Navy headquarters reached Nakajima's Koizumi facility on September 14, 1943, carrying specifications seeming designed more to inspire than inform. Kenichi Matsumura read the requirements twice before placing the document on his drafting table, understanding that Admiral Yamamoto's staff had essentially commanded his team to defy the laws of physics within an 18-month window. Maximum speed, 370 miles per hour, faster than any existing heavy bomber anywhere. Service ceiling, 33,000 feet, high enough operating above most interceptors. Range, 4,600 miles with reduced ordnance, sufficient reaching America's west coast. Bomb capacity, 8,800 pounds maximum, enough devastating industrial targets. The blueprints looked ambitious, almost naive in their scope. Men who'd never wrestled with power-to-weight calculations or aluminum inventory constraints had drawn up these specifications. Yet Matsumura possessed something they lacked: 18 months of hands-on study with captured B-17s, careful analysis that had yielded a stunning realization. Japan's whole approach had been fundamentally backward. The nation had mimicked American hardware while completely missing the American way of building it. The new bomber, christened Gan Renzan or Mountain Range, would break completely from the DC-4E template. Instead, it would adopt the underlying design philosophy that made American aircraft so devastatingly effective. That autumn, Matsumura's team burned midnight oil session after session, systematically abandoning every principle that had governed Japanese aircraft engineering since the 1930s. The old Japanese approach worshipped individual craftsmanship and perfect components, birthing aircraft that dazzled as engineering showcases but turned into manufacturing catastrophes. American designers thought differently. They integrated systems methodically and obsessed over production speed, building aircraft that were adequate enough to manufacture by the thousands. The G-8N that emerged from these grueling months bore almost no resemblance to Japan's previous bombers. The design stripped away complex curves in favor of clean, functional lines. That troublesome twin tail that had haunted the Shenzhen's stability disappeared, replaced by a single vertical stabilizer. The wings mounted mid-fuselage, a choice that offered structural efficiency while giving maintenance crews actual room to work. Every single component followed a ruthless priority system. Reliability first, then performance, then how easy it was to manufacture. This inverted the entire Japanese aircraft philosophy that had existed for over a decade. Selecting the right engines became absolutely central to whether this whole program would succeed. Rather than retrofit existing motors, Matsumura pushed Navy procurement to develop an entirely new power plant specifically designed for the G-8N, the Nakajima NK-9KL Homar Radial. Each would deliver 2,000 horsepower at combat settings, giving the aircraft 8,000 total horsepower. An aircraft that would tip the scales at 38,360 pounds when empty would finally achieve that precious American standard power-to-weight ratio while actually surpassing American performance. The Homar engines embedded lessons torn from dismantled Wright Cyclone engines, prioritizing reliability over peak power. The cylinder cooling fins used designs simple enough for mass production, while internal parts met tolerances that married precision with producibility. Supercharging systems were tuned for high-altitude work, delivering full thrust at altitudes where enemy fighters gasped and fell back, unable to maintain formation. The airframe construction abandoned those expensive forgings and custom machining that had made the Shenzhen impossible to produce cheaply. G-8N wing spars utilized aluminum extrusions rolled on standard mills with reinforcement concentrated where stresses peaked rather than spread throughout. Skin panels came designed for field replacement using basic tools, letting mechanics repair combat damage where the aircraft landed. The electrical architecture reflected hard-won understanding of combat maintenance. Standardized connectors and color-coded wiring meant no guesswork during emergency fixes, while accessible routing let mechanics track problems quickly instead of spending days hunting through complex networks. Power distribution followed proven American bus systems instead of the Byzantine switching arrangements that had transformed Shenzhen electrical work into a specialist's nightmare requiring endless troubleshooting. Fuel system design balanced survival with workability. Self-sealing tanks packed rubber bladders that squadron mechanics could swap out, while pumps and valves sat where anyone could reach them during regular service. The setup allowed precise fuel management for deep-range missions while dodging the complicated automation that had created endless failure points in earlier designs. Defensive gun placement mixed firepower with structural soundness, avoiding those weight penalties that had crippled previous Japanese bombers. Gun mounts used standardized hardware that could accept various weapons types, while ammunition feeds relied on mechanical systems that worked reliably even under violent aerial maneuvers. The installation delivered firing coverage all around without creating drag or weight issues that would rob the aircraft of performance. The first G-8N prototype rolled out from Nakajima's final assembly hangar on August 23, 1944, its silver aluminum hull shining brilliantly beneath work lights that had burned continuously for 3 straight months. Matsumura personally walked through the pre-flight checks, inspecting systems born from 4 years of accumulated wisdom about what made aircraft prosper in actual combat. Test pilot Captain Takeshi Shirani took the controls on October 23, 1944, and reported handling that surpassed every expectation. 368 miles per hour at 26,245 feet proved the design calculations had been sound. Japanese manufacturing could now match American performance. The service ceiling reached 33,465 feet, soaring well beyond the altitude band where most interceptor fighters remained effective. Range trials delivered equally impressive numbers. 4,639 miles of maximum range confirmed during carefully controlled fuel consumption tests. The G-8N could finally strike targets on America's western coast and limp back to bases in the Mariana Islands, granting Japan the strategic bombing reach promised ever since Pearl Harbor planning had begun. Yet even as the third prototype wrapped up acceptance testing at Koizumi Airfield early in 1945, the strategic landscape justifying this entire program was crumbling irreversibly. American B-29 superfortresses methodically pulverized Japanese industry, while carrier aircraft roamed freely over home islands. The aluminum destined for G-8N factories was being redirected toward defensive fighters, offering faster protection against bombing raids that were reducing Japanese cities into charred ruins. Merely 4 G-8N prototypes reached completion before Japan's surrender terminated everything. The aircraft that had finally solved Japan's strategic bomber dilemma had materialized far too late to reshape the war's conclusion. Engineering mastery rendered meaningless by industrial mathematics that no technical wizardry could overcome. Matsumura observed the fourth prototype taxi toward its final parking spot on August 10, 1945, acutely aware that American technical personnel would arrive within days to study what Japanese engineering could achieve when unburdened from the requirement of imitating foreign designs. The G-8N embodied everything Japan had absorbed about constructing aircraft correctly, yet acquiring that knowledge had consumed too many years to matter. The surrender message crackled through radio speakers at Koizumi facility precisely at noon on August 15, 1945, carrying Emperor Hirohito's voice announcing Japan's unconditional surrender. Kenichi Matsumura remained standing inside the engineering hangar beside the fourth G-8N prototype, watching his 200 specialists confront the reality that 4 years of relentless development had terminated in complete national defeat. B-29 superfortresses continued their merciless destruction of Japanese manufacturing capacity beyond the hangar walls. Their contrails marked altitudes the G-8N could theoretically reach but would never operationally challenge. The irony struck with crushing force. Japan had manufactured a strategic bomber matching American capabilities precisely when American strategic bombers finished destroying Japan's capacity to build aircraft in significant numbers. The program's ultimate collapse, reduced to devastatingly simple arithmetic, burned into Matsumura's mind. 4 G-8N prototypes against 12,731 B-17s and 14,000 B-19 flying fortresses constructed by American industry. 4 aircraft symbolizing the zenith of Japanese engineering versus American production lines that delivered more bombers monthly than Japan had assembled during 4 years of all-out effort. American technical intelligence personnel arrived at Koizumi on September 3, 1945, led by Colonel Harold Watson, directing Army Air Force Technical Intelligence Operations. Matsumura personally guided the examination of the G-8N prototypes, detailing design choices and performance characteristics to American engineers approaching with professional intrigue rather than victor's arrogance. The captured German and Japanese aircraft they catalogued represented technological peaks that had surfaced too late to alter the war's outcome. Colonel Watson's appraisal, registered in technical reports locked away for generations, conceded the G-8N's remarkable accomplishments while emphasizing the industrial constraints that had condemned it. Maximum speed of 368 miles per hour surpassed early B-29 performance. The service ceiling of 33,465 feet matched American heavy bomber altitudes, while 4,600-mile range would have permitted continental strikes from Marshall Island bases. Performance numbers alone conveyed only partial truth. Watson's calculations determined that producing a single G8N consumed roughly 42,000 man-hours of experienced labor versus 18,000 man-hours for a B-29 rolling off Boeing's mechanized assembly lines. Japanese craftsmanship yielded technically superior individual parts, yet American mass production delivered strategically winning aircraft through overwhelming numerical advantage. Material analysis exposed far starker disparities. Each G8N prototype required 8.7 tons of aluminum alloy, while American heavy bombers averaged 6.2 tons through systematic structural optimization. Japan's complete aluminum output in 1944 crested at 142,000 tons, theoretically sufficient for 16,000 G8N bombers if nothing else received production resources. American aluminum production during 1943 exceeded 920,000 tons, simultaneously feeding fighter production, bomber production, transport aircraft, and civilian manufacturing without conflict. Matsumura found himself explaining to American questioners the philosophical differences molding Japanese aircraft engineering throughout the entire conflict. The traditional Japanese approach idolized perfect individual components, producing aircraft representing manufacturing precision masterpieces, yet production nightmare complexity. American engineering integrated adequate components into effective operational systems, generating aircraft that semi-skilled workers using standardized procedures could manufacture. Engine development comparisons particularly illuminated American technical analysts studying Pacific War lessons. The NK9KL Homar radials in the G8N generated 2,000 horsepower each through supercharging representing cutting-edge Japanese technology, yet demanded complete overhauls every 120 flight hours because of metallurgical limitations in high-stress elements. Wright R-3350 Cyclones in the B-29 produced 2,200 horsepower while operating for 400 hours, separating major overhauls through systematic reliability engineering, favoring operational availability over peak capability. Manufacturing philosophy differences touched everything. G8N wing spars came machined from solid aluminum blocks using precision tooling, demanding hours of setup for every part. B-29 wing spars assembled from aluminum extrusions and sheet metal stampings mass-produced using automated equipment operated by minimally trained workers. Japanese techniques created structurally superior components, but American techniques produced adequate components in volumes overwhelming any performance edge. Maintenance requirements analysis exposed operational truths invisible during peacetime development. G8N systems demanded specialized tools and experienced mechanics for basic maintenance, making squadron field repairs impossible under combat pressure. B-29 systems were engineered for maintenance by mechanics receiving fundamental training using standard tools present at any forward position. A damaged superfortress returned to combat within hours, while a damaged G8N required weeks at specialized maintenance sites. By October 1945, American technical personnel had completed their Japanese aircraft documentation and formulated conclusions influencing military procurement for following decades. Technical brilliance absent industrial capacity meant nothing strategically. The world's most advanced aircraft could not compensate for fundamental manufacturing limitations and resource allocation shortfalls. Matsumura's final conversation with Colonel Watson occurred beside the fourth G8N prototype on November 8, 1945, as American crews prepared shipping the aircraft to Wright Field for complete analysis. Discussion centered not on technical specifications but systemic determinants of the war's outcome, despite individual Japanese aircraft accomplishments. Industrial warfare's devastating mathematics had rendered engineering brilliance irrelevant. More B-17 flying fortresses had fallen over Germany, 4,750 aircraft, than Japan had manufactured of all heavy bomber types across the entire conflict. American factories replaced combat losses faster than Japanese factories manufactured new aircraft, creating mathematical impossibility that technical mastery could never overcome. Watson's final report, entered in classified documents shaping Cold War American industrial warfare understanding, stressed lessons extending beyond aircraft development. Winners built not superior weapons, but adequate weapons in overwhelming quantity. The G8N Renzan represented what Japanese engineering accomplished, freed from resource constraints, yet constraints constituted modern warfare's fundamental reality. Matsumura watched the fourth prototype vanish into the American transport aircraft hold. Recognizing his team's greatest work would become museum display instead of operational weapon. 4 years of concentrated development had created an aircraft potentially changing war trajectory if manufactured in volumes Japan could never achieve. The delayed lesson was straightforward. Possessing the blueprint meant nothing.